Welcome back. In our previous video, we learned about quantum logic gates for single qubit states. Now let us learn what is a unitary transformation. The transforming gates we described X gate, Z gate, Hadamard gate, phase gate. They perform what is called as unitary transformation on the qubit states. What do we mean by a unitary transformation? A matrix U is called unitary matrix if it satisfies equation 24. U conjugate transpose U is equal to U conjugate transpose is equal to I, where U dagger symbol is representing the transpose conjugate. You transpose the matrix, you replace the elements by their corresponding conjugates, complex conjugates. That is meant by the transpose conjugate. So when you multiply a matrix with its transpose conjugate in any way, any order, when you get an identity matrix, that is to say the diagonal elements are 1 and the non-diagonal elements are 0, such a matrix is referred to as a unitary matrix. On the block sphere, a unitary transformation on the qubit state corresponds to changing the position of the block vector from one point to another on its surface, which also means that the inner product or the normalization condition Bragg psi ket psi is equal to 1 even after the transformation. The length of the vector is constant even after the unitary transformation. Now let us consider an example for the above statement. Now when you perform a Hadamard transformation on the state ket 0, so the ket 0 is situated at the north pole and the Hadamard transformation on ket 0 gives you 1 by root 2 ket 0 plus ket 1, which is the plus state. So it rotates it by 90 degrees. It is still on the sphere, block sphere. So the Hadamard gate on 0 rotates the block vector from north pole to equator by an angle of pi by 2. So any transformation, any unitary transformation on the qubit will just move the point from one point of the sphere to another point of the sphere. The length of the block vector remains a constant under unitary transformation. Now verify that X gate, Z gate and phase gate, S gate are unitary transformations. Now X is equal to, the matrix representation is 0, 1, 1, 0. Its transpose conjugate is going to be the same because you have interchanged its rows and columns and replaced its elements by its corresponding complex conjugate. You have the same thing. And clearly under matrix multiplication, X dagger X is equal to X X dagger, you get the identity matrix. Hence the X gate is a unitary. Next, for the Z gate, even in this case the transpose conjugate is same as before, and doing the multiplication gives 2 cross 2 identity matrix. The Z gate is also unitary. Now the last case, the phase gate or the S gate, here you notice how there is a sign of change because you have transposed the matrix, interchange rows and columns, and replace the elements by their corresponding complex conjugate. One complex conjugate is just 1, but I has to be replaced with minus I, and multiplying them yields a 2 cross 2 identity matrix, implying S gate is unitary. Now a homework problem would be to find or to verify that the Hadamard gate is also a unitary matrix. Now quantum gates for 2 qubit states. Now we shall study the unitary transformation on 2 qubit states. The basis states in the case of single qubit states are just 0 and 1. The basis states in the case of 2 qubit states, as mentioned in my previous videos, would be ket 0 0, ket 0 1, ket 1 0 and ket 1 1. The basis states of 2 qubit states can also be written using the following notation. So you either write it separately or combine them or separate it by a comma. It depends on the convenience of the person. One may choose any notation for writing 2-qubit states. Now, a 2-qubit gate would be the controlled NOT gate or the C NOT gate. In the C NOT gate, one qubit is taken as control, the other is taken as the target. This gate works in the following manner. When the control qubit is 0, the target qubit is unchanged. When the control qubit is 1, the target is flipped. So as long as you have the control qubit to be 0, nothing happens. But when the control is 1, then you switch the target. Now, first let us the first qubit, let it be the control, and the second qubit be the target. So in this example you can see, so the first is the control and the second is the target. So the first is 0, so nothing happens. So after the C naught transformation, it is still 0 0. In the second example, 0 1, the control is still in 0, so nothing happens. It after the C naught transformation, it's just 0 1. But in the third example, you notice that the control is 1, in which case the second qubit has to be flipped, the target has to be flipped. So 1 remains 1 and 0 is flipped to 1. So 1 0 under C naught transformation becomes 1 1. When you have 1 1, again the control is in 1, so the target has to be flipped. So 1 1 after C naught transformation becomes 1 0. So this is the action of C naught gate on 2-qubit states. So this is the circuit diagram for the C naught gate. The control qubit is represented by a shaded circle, while the target qubit is a circle with a plus mark. So that's the symbol you can see there. If the first qubit is target and the second is control, then you write it the other way around. You put an open circle near the target and a closed shaded circle with the second one, which is the control. So these are the examples. So the first qubit is the control and the second one is the target. So 0 remains 0 0 0. So when you have the control to be 1, the target has to be flipped. So this is the truth table for the C naught gate. When both are 0, the output is 0 0. When you have one qubit as 0 and the other one as 1, it is 0 1. When the first qubit, the control is 1 and the target is 0, the target has been flipped, so you have 1 1. And when the control is 1 and the target is 1, since the control is 1, the target has to be flipped, it becomes 1 0. The other gate for a 2-qubit quantum 2-qubit state is the swap gate. So a swap gate is a unitary transformation on a 2-qubit state which interchange the qubits. So this can be generated by using 3 C naught gates as shown in the figure there. So A and B are the 2 qubits. So first you have control for the first and target as the second. Then you have first to be the target, second to be the control, and thirdly you have control for the first and target for the second. So these 3 C naught gates together act as a swap gate. So what would they do? They would interchange A and B. A would become B and B would become A. And that the second figure at the bottom shows the circuit diagram for a swap gate. Now the problem is to calculate the swap gate transformation on the following 2-qubit states: 0 0 0 1 1 0 and 1 1. So when you have 0 0, interchanging them is just 0 0, and if you have 0 1, interchange them, it becomes 1 0 under swap gate transformation. Just interchange the first and the second qubit. 1 0 becomes 0 1, 1 1 is 1 1.